We are now in linear transformations. There will be several videos about this. Normally it's not complicated, it's quite straightforward, even though there are some computations around here. So in this particular video we will see the definition and a couple of examples, illustrations of what is a linear transformation. You don't need to remember those examples. The only thing that is crucial is the definition and one or two properties that we are going to see. So first thing, since we are talking about linear transformations, it would be good to know what is a transformation. So basically this is a reminder of a definition, transformation, or a function. So here we have a function between two linear spaces, V and W. So transformation is a function that transforms objects that are living in V. It does something to them and transforms them into objects living in the linear space W. So a caricature of that is if you take meat cubes or steak and then you have this mincing machine that produces minced meat. So this is a transformation. You had one object at the entrance and then the transformation did something to it and it transformed it into another object. So that's pretty much what the function is and what the transformation is. It just transforms objects from one linear space into objects from another linear space. Another example, if you have nut grinder, let's say you have some nuts and then this process here, the transformation transforms the nuts into a powder. So that's a transformation, that's a function. Now you are used to functions of one variable. Here we are going to deal with functions having several variables, x1, x2, x3, xn, and they will be transformed into other objects, maybe other vectors, maybe real numbers, maybe matrices, maybe polynomials. So it depends all on transformation itself. What is important is to remember that transformation transforms objects from one linear space into objects of another linear space. So that's pretty much a general definition. So now, particularly a linear transformation, so it's a transformation, so it transforms objects living in V into objects living in W, but it does so in a specific way, and the property of that transformation is that it is linear, and these are the two conditions for a transformation or a function to be linear. So if you add two inputs, the transformation of summation of two inputs is summation of the outputs. Simple. And if you multiply u, an input, by a constant, well, the transformation of that is constant times the image of u. So these are the two conditions that will decide if a function or transformation is linear or not. So we are dealing with linear transformations, so our transformations must satisfy these two conditions. As a consequence, you will realize that t of 0 will be 0. So that's one of the nice consequences of linearity, is that 0 is always mapped to 0. So image of 0 is 0. Obviously, there are other functions that are not linear that do that. X squared does that, sine does that, but what we are saying is a function that is linear will transform 0 into 0. Okay, so that's something important and useful. So another thing that we are going to see later on is that when our spaces are finite dimensional, that means that the basis has finite number of elements there, then the linear transformation can be associated to a matrix. So basically, linear transformations between finite dimensional spaces can be represented by matrices. So that will be subject of another video, how we do that, and that will be a lot of fun. A consequence of linearity is when you have a linear space V with a finite basis here, V1, V2, Vn. So every object is obviously a linear combination of the basis vectors. So when you apply linear transformation to vector V, so you just use the definition that the composition you have of V in basis vectors, so this linear combination here. So by linearity, we can break it into this. So the constants go out and all these plus signs are distributed. So you have this linear combination here. So you realize that the image of V, when you decompose V as a linear combination of basis vectors, is actually a linear combination of images of basis vectors. So that's something that we are going to use a lot. That's nice property. So what we need actually mostly is to know the action of the linear transformation T on basis vectors, V1, V2, Vn. You see the C1, C2, Cn, those are the coordinates of V in the basis B. You see, there are coefficients here. So they are repeated here also. So what is really important is the image of basis vectors. So that's something we are going to use a lot in a different video. So that's a property that comes from linearity directly. So we know now that when our spaces V and W are finite dimensional, we can build a matrix that represents a linear transformation. So these matrices that represent the linear transformation will depend on the basis we chose for V and W. So when we choose standard basis for V and standard basis for W, then the representation matrix will be called standard matrix because we are using standard basis. But if we use a different basis for V that is not standard, or for W, or for both, then we will have another representation matrix that will be different from this one, and it will be relative to these two bases of V and W. So we will do a different video only on that. So there will be one video how to build standard matrix and another one how to build representation matrix relative to different bases. It's a lot of fun. So what matters is to remember that when we have finite dimensional spaces, and our linear transformation can be represented by a matrix. So that will be subject of a different video. This is just an introduction. So one way to do it, and we will do it in a separate video in detail, how do we build standard matrix? We just apply the linear transformation to basis vectors. So this is a linear transformation that is given to us. We could verify it's linear, but we don't need to. We are dealing with linear transformations, so we will have linear transformations given to us most of the time. So how do I build standard matrix? I just applied this linear transformation to standard basis vectors. So vector 1, 0, I apply the transformation, I get this as an image, 1, 1. And standard basis vector 0, 1, I applied the linear transformation given here to that vector. So x is 0, y is 1, and I get the image negative 1, 2. So all I do is just put those images into a matrix. So that's called a standard matrix. So we will have a separate video only on that, how to build it and how to use it. So you see it's not complicated at all. You just plug the basis vectors into the definition of the transformation that is given to you. It is important to realize that some transformations are linear and we will deal with them, but there are other transformations that are not. Obviously, let's say functions, sine, cosine, tangent, exponential, they are not linear, so we know that. But also, 1 plus x is not linear. So any translation is a nonlinear transformation because it doesn't satisfy any of the two conditions actually. Another way to see it, every linear transformation maps 0 to 0. So here if you put 0, then you'll have 0 plus x0. x0 is some vector, let's say 1, 1. So you are shifting everything by 1, 1. So like here. And then you are adding a vector x0, or let's say in our case 1, 1, and then you're shifting everybody. So that's a translation and that's not linear, even though the graph is a straight line. So linear transformations map 0 to 0, mandatory. They are not the only people, not only functions doing that, but or any linear transformation must map 0 to 0. There's another transformation we are used to, the computation of the determinant. So this transformation takes as an input a square matrix, and it does something to it, to its components, and it produces a real number. So the computation of the determinant, we know it is not linear. What is interesting is to see that our transformation is taking as input matrix, and it transforms matrix by some procedure. We know how to compute determinant by now. It transforms the matrix into a real number. See, so it associates to our square matrix a real number that is determinant. So that's a transformation, but it's not linear. Okay, so you see now that we can have transformations that work on other objects different from just numbers and vectors, matrices, polynomials, other functions. So some examples of linear transformation that you are used to: derivative. So it takes as an input a function that is differentiable, and it associates to it another function that could be continuous or not. So you have a transformation that is derivative or differentiation of a function, and it takes a continuous function as input and gives you another function, the derivative, as output. So that's a linear transformation because it satisfies the two conditions of linearity. Integral also, so operation of integration is linear. For those who are studying differential equations, your Laplace transforms are linear. So you have different type of integration that in this case is linear. Also, something weird, you have a transformation that works, let's say, on 2 by 2 matrices, and it transforms them into real numbers in this way. So it's just summation of the elements. So that's a linear transformation. It's not really useful, but it's a linear transformation. So you see, as an input, I had a matrix, and then we transformed it in a certain way to get a number. And this is the way we transformed it. We just added the components. Something similar we can do with polynomials. So I have polynomial of degree n, and this linear transformation transforms the polynomial of degree n into a real number by adding the coefficients. So these transformations have inputs, let's say polynomial, and output is a real number. Here input was a matrix and output was a real number. What matters is the property of linearity that is respected, the two conditions. So what I want you to see is that linear transformations, they can transform objects that are not just numbers and vectors. They can transform matrices, functions, polynomials into other objects. Could be real numbers, could be vectors, could be other polynomials. So the whole goal here is to present just examples, so you know that these linear transformations are working on numbers, vectors, matrices, polynomials. So other stuff, it's not just simple numbers. Here you don't need to remember any of these transformations. This is just for example and illustration purposes. So we have reflections here, different reflections. So this one is about y-axis, illustrated here. So what happens is that vector xy becomes negative xy because it's just reflection about y-axis. So this illustration in itself is cute, but it's not so important to us. What matters is the definition of the transformation. And what you need to pay attention and what will be useful for the next video is how to build the standard matrix. Well, it's very simple. You apply this linear transformation here to the basis vectors of R2. So standard basis vector is 1, 0, and 0, 1. So you apply the linear transformation to standard vector 1, 0, and you get the result. And you apply the linear transformation to standard vector 0, 1, you get the result. And then you just put those results as column vectors of a matrix. So that's how you build the standard matrix. Take the first result, put in first column, second result in the second column. And then we repeat the process for different other reflections. So reflection about x-axis, so x remains the same, y has a negative sign in front. So I applied that transformation to both basis vectors, so 1, 0, and 0, 1. These are the images, and the first image I put it in first column, second image in the second column, and this is my standard matrix. So that's how we build them. You will notice that some of these standard matrices are invertible. That will mean that linear transformation is invertible, and some other are not. That would mean that linear transformation in question is not invertible. So that's fine, or everything is fine. So here reflections are invertible. So now more examples. Reflections in 3D. So about the planes, different planes. So the formula is given here. To build a standard matrix, we apply this linear transformation to the basis vectors of a standard basis of R3. So 1, 0, 0, 0, 1, 0, 0, 0, 1. So just apply it, get the result, put in the column. So this is the standard matrix associated with the reflection about xy plane. And this one is also invertible. So that means that this linear transformation is invertible. That's all. And then we proceed similarly with others. So what matters here, you are given the linear transformation in the question. You need to build a standard matrix. How you do it? Apply this linear transformation to the standard basis, so the vectors from the standard basis of R3. That's all. You do that, put the results in columns, corresponding columns, and that's it. You have your standard matrix. Very simple. So this transformation is orthogonal projection on axis x and y. Okay, so you have one is for x, the other one is projection on y. So what happens here? Every vector is projected on x-axis, so its y component is 0 and its x component remains the same. So that's the linear transformation. You don't need to remember this, it's just an illustration. So the projection on x-axis, what happens? X remains the same, y becomes 0. So how do I build standard matrix? Simple. Apply this linear transformation to basis vectors for R2, so standard basis vectors. So you apply it and you get these two outputs. So first one you put in first column, second one in second column, and you have your standard matrix for the linear transformation. So this matrix is representing the projection, so the linear transformation, projection on x-axis. And you see this matrix is not invertible, which means this operation here is not invertible. That's fine, there's nothing wrong with it. Similarly, for the projection on y-axis, x becomes 0, component x, and component y remains the same. So you apply that linear transformation to the standard basis vectors of R2, and you get the results, and you put them in the columns. So again, it's not invertible, it doesn't need to be. It's just a linear transformation. These are just illustrations, no need to remember this. Then in 3D, you have projections on different planes, similar procedure, depending on the plane. So one of the component dies, and then you apply this transformation to basis vectors from standard basis of R3. One at a time, you start with the first one, put the result in the first column, second one, put the result in the second column, third one, put the result in the third column. So that's your standard matrix. So you see again, projection is not invertible. It doesn't need to be, it's fine. It's just a linear transformation. Another one is when we make a rotation by a specified angle. Let's say I want to rotate things, the vectors, by 20 degrees counterclockwise. So this direction, and the angle is 20 degrees. So this is the formula, how we get the components. So basically, cosine theta and sine theta and everything, theta is 20 degrees, so I compute this will be a number, this will be a number, this will be a number, this will be a number. So I'll have some type of a matrix with only numbers inside, okay? Now we can show that this matrix is invertible because the determinant is 1. So rotations are invertible. Angle is specified at the beginning. So this is just one other illustration of linear transformation. You don't need to memorize it, just an example. Then you can have rotations around different axes in R3, so similar procedure. These things are given here, so you just apply this transformation to basis vectors from standard basis of R3, and then you put the results in columns, and that's it. Obviously all of these matrices are invertible because it's just a rotation, so that's invertible, but it's fine. Here we have two transformations that are similar. One is contraction, so you're contracting, let's say, a square or a vector, you just shrink it. And the other one is dilation, when you extend the vector or you extend some square or whatever. So again, you extend it by a certain factor. So if the factor is between 0 and 1, then you are contracting, you're shrinking it. And if the factor is greater than 1, then you are extending. And the matrix is the same, standard matrix is the same. So you have other illustrations of that. So the idea here is just to show you that these transformations also are linear. So there's a lot of useful linear transformations actually. That's the idea here. You don't need to memorize them, but it's just nice to know. So here is contraction and dilation in R3. So you're just extending or shrinking a vector. So you see this is like K times identity matrix. Obviously, this is invertible when K is different from 0. So these are just examples, you don't need to memorize them. Other type of examples is when you compress along one axis. So again, all these are useful transformations in other subjects. So these are obviously invertible when K is different from 0. So the idea is just to see that you have a lot of transformations that are actually linear, and these transformations are useful. You have a shear transformation also given by this formula here, so apply it again to standard basis vectors from R2, and then you get this matrix here, and it happens to be invertible for any K because it's upper triangular or lower triangular, and diagonal entries are 1. So that's the idea of all these tables, is just to show you that we have a lot of linear transformations that are very useful. We don't need to memorize them, but we need to be aware that they exist, and we need to be aware that linear transformations can be applied to vectors, but also to matrices, to polynomials, and the output could be a vector or a matrix polynomial or real number, depending on the situation. So in each case, the transformation is given, so we know what is the transformation, and then we apply it to the standard basis vectors, and we get the standard representation matrix. Here is a weird one. So this linear transformation works on polynomials of degree n, and then multiplies them by x and gives us back polynomial of degree n plus 1. So we take polynomial degree n, and the linear transformation is just multiplying that polynomial by x. So you get a polynomial degree n plus 1 with no constant term. So that's a linear transformation. The proof is here. So it doesn't need to be specifically useful for something, but it is a linear transformation. So you see, we have as an input a polynomial of degree n, and then as output turns out to be a polynomial degree n plus 1. And the rule to produce those polynomials is just to multiply the input by x. Somebody could create another one where you multiply the input p by x squared, and then you'll get polynomials of degree n plus 1. Wow. That would be also a linear transformation. Another weird one, we can pick a vector v0, let's say in R2 vector 1, 1 for fun, or any other vector you like, doesn't matter, you pick one. And then the linear transformation will be defined as a dot product between your cherished vector v0 and all the other vectors in R2, let's say. Here is Rn, but doesn't matter. So that operation, the dot product with a fixed vector v0, is a linear transformation. And here is the proof for two conditions to be satisfied to be able to call a linear transformation linear. Okay, so these are two conditions of linearity. So you can have very, very weird stuff that are linear transformations. All they need to satisfy is the two conditions of linearity. Another cute one is the transpose of a matrix, and you have the proof here, verification of both conditions of linearity. So operation of transposing a matrix is linear. Wow. We already know that computing determinant is not linear. Also, if a matrix is invertible, we know that operation of inverting a matrix is not linear. But this is just a cute observation. So the goal of this was just to show you that these linear transformations act on different objects as input and can give you different objects as output. That's all. What you need to remember is just the definition. The definition of linearity. How do you know that function is linear or transformation is linear? When it satisfies both of these conditions. These are linearity conditions. As a consequence, if you write some vector v as a linear combination of basis vectors, then the image of v under a linear transformation is given by this linear combination here of images of basis vectors. So that's very important to remember. Also, it is important to remember that t of 0 is also 0. So 0 is mapped to 0 by any linear transformation. So those are the only things that we need to remember for now, the definition and this cute property. You can go to chapter 8 of the book and solve some problems. They are not complicated. It's just verification of linearity pretty much for different types of inputs and different types of outputs. The goal is again just to remember the definition and the properties of linearity and to realize that linear transformations, they act on different types of inputs, not only vectors and numbers, they can act on polynomials, they can act on matrices, and the outputs could be other polynomials or numbers or matrices or whatever. So just be open to that. That's the goal here. And we will be creating other videos where we explain explicitly how to build these representation matrices, standard matrix and other matrices. So that will be subject of a different video.